It's a pleasure to introduce Lorenzo Mazzieri, which will talk about classification problem from static metric with positive cosmological constant.
Okay, thank you very much. Thank you very much to the organizer for having me here. Actually, it's always a pleasure to visit Vienna and to be here with this very distinguished community. Actually, okay, I'll try to present some result that I've obtained mainly in collaboration with Stefano Borghini from Trento and Piotr Kruschel from Vienna. Okay, so I mean the problem is an old one. So I try to give a quick introduction, even though basically I think most of you already know this introduction, this introductory material. It's convenient for me also for later purposes. So essentially, I focus on three-dimensional static triples. Okay, by this I mean a three-dimensional Riemannian manifold, okay, and a smooth function U, okay, as non-negative smooth function U, okay, which is the lapse function. So we call MGU a static triples if these three objects satisfy the following system. So you have, so for U times the Ricci tensor of G, where G is a Riemannian metric, a Riemannian 3 metric, is equal to the Hessian of U plus lambda, and here is the cosmological constant U times G, okay, and this is on M3. And then you have a scalar equation for U, so essentially U is an eigenvalue for the Laplacian of the metric G, and this also is satisfied on M3. And then U is equal to 0 on the boundary of M3. Actually, the boundary is the only place where U vanishes, and U, let's take U positive in the interior just to avoid ambiguity. Okay, so this system starts, okay, and the constant lambda is the cosmological constant. Okay, in the following, it will be always be normalized to be 3, 0, or minus 3. Okay, this is our choice of normalization. We will be mainly interested in the result in the case with positive cosmological constant, so with lambda equal to 3. So everyone knows that as soon as you have a static triple, you can produce a static solution to the Einstein equation, namely a four-dimensional Lorentzian manifold, which is just R times M3, okay, with a Lorentzian metric, which is just gamma equal minus U square dt square plus G, okay, and this Lorentzian manifold actually obeys the static vacuum Einstein equation, namely eventually with cosmological constants. So Ricci gamma minus R gamma over 2 times gamma is plus lambda times gamma equal to 0. So these are the vacuum Einstein field equation, okay? And this is a static solution to the vacuum Einstein field equation. So, sorry, yeah, you're right. It's minus lambda, sorry. So because I already said, thank you very much. Yeah, in general it's like that. And then we focus mainly in the case lambda equal to 3. But yeah, the observation comes really appropriate because I want to start first with a little warm up in the case lambda equal to 0. So where basically most of the results are known. So lambda equal to 0, you have some model solution, okay? Let me talk about model solution. Or maybe, yeah, model solution. okay, in lambda equal to 0. So of course you have the easiest one is the Euclidean space, okay. So it's the flat Euclidean space where M3 is equal to R3, G is just dr square plus r square GS2, and U is just identically equal to 1. And then you have the Schwarzschild metric. Okay, I mean, I consider just the space-like part of the Schwarzschild metric. Here's the horizon. Okay, and of course, this is another rotationally symmetric solution. So you have M3 this time is equal to R3 minus a ball, a three-dimensional ball of radius 2m, where m is a positive number, which will be referred to as the mass of that solution. And then you have the metric Gm, which is, as I said, rotationally symmetric. So dr square divided by um square of r plus r square gs2. And um is it only depends on the radial variable, and is just the square root of 1 minus 2m over r, okay? So essentially, as you can see, when m is going to 0, you recover the solution. So this one should be think of as the zero mass model, okay, for the problem. And of course, there are some very special features of the boundary. In the case you have one, so the boundary it can be easily checked. That is a minimal surface, stable minimal surface. It is even more. It is actually a totally geodesic hypersurface, totally geodesic two sphere, okay, inside this ambient manifold, okay, and it is you have a theorem here, which is in its first instance it was due to Israel. Let's go a black hole uniqueness theorem, and it has been revisited afterward by several authors with improvements, of course. Let's call it black hole uniqueness theorem. Okay, so it states that actually the only if M3 GU is a vacuum static tripole, with a zero cosmological constant, which is asymptotically flat. Okay, let me skip on this definition because it has been given several times. So if it is asymptotically flat, then the only solution are the two model solutions, so either flat Euclidean space or Schwarzschild. With positive mass. Okay, so this is the statement that we'd like to investigate, even in the case of please. Sorry. Yeah. Sorry. Yeah, U is going to U is going to 1 at infinity. So yeah, in the asymptotically flat, it's hidden in my definition of asymptotically flat static tripole. So you have that U is going to 1 at infinity. U is an harmonic function in this case. In the case lambda equal to 0, U is an harmonic function, so it is 0 there. It cannot reach. I mean, it cannot achieve a maximum. At a given point here, because otherwise it would be constant by the strong maximum principle. So the only way that it is going to achieve the maximum at infinity, you normalize in such a way that U is 1 at infinity. Yeah, it could be unbounded, but yeah, in this case yeah. Okay. Yeah, like in the boost case, it's unbounded. Yeah. Okay, so there, as I said, there are. I mean, the first result in this direction, the first proof of this kind of statement is due to Israel, even though, I mean, there were extra assumptions made on the topology of the level set of U. But then there have been several other different proof and improvement by Muller-Zumhagen, Robinson, Seifert, and then by Robinson, and then a very famous argument by Banting and Mazzoud-Ulalam that I will describe briefly because it matters for us. And then recently also we managed to give another alternative proof in the three-dimensional case together with Virginia Agostiniani using monotonicity formula along the level set of U. Okay, so I will try to convince you that actually the problem of classifying this solution is very much related to the problem of understanding the concept of mass and having a result, especially a rigidity result in the theorem concerning the mass. It's crucial also for proving classification result for a static metric. As an instance of this fact, of this phenomenon, let me describe it for you briefly. The proof that I guess it's the most advanced one of this statement, the one given by Banting and Mazzoud-Ulalam. Okay, so there is this proof using positive mass theorem. So let me. Banting, Mazzoud. Okay, in 1987. So the sketch of the proof is the following. So you start with your asymptotically flat triple, okay, and at the beginning you imagine to have several component of the boundary. A priori, the situation should be like this, okay, and then what you do is, since these horizons are totally geodesic, you can double your thing, and what you get is something like this. So now we have two. Oh, sorry. Asymptotically flat end. So at the beginning you have so you have the double of your manifold, the double of your metric, essentially. And then what they do actually is to perform a conformal change of metric. So you have a conformal change. So you consider V to the power n4 over n minus 2, okay, 4, times G double. You call this G double twiddle. And the new metric, the new conformal metric, actually looks like this. So you have the asymptotically flat end, the original one slightly perturbed, and the new one you have something like this. Let me try to. Okay, so here a priori you compactify the point. Here are where your horizon were actually, and in the new metric. Yeah, sure. I think so. Okay, so then you can add a point here to compactify. You have a very nice asymptotically flat manifold. So your double manifold with the metric GD twiddle, okay, is now asymptotically flat. It has non-negative scalar curvature, okay, and it has zero mass. So the mass, the IDM mass of this new metric is 0, and then you can invoke a very powerful tool, which is the rigidity statement in the positive mass theorem, okay? And this tells you that the whole thing that you get is flat actually, okay? Because if it is there's zero mass, by the rigidity statement of the positive mass theorem, you have that these things must be flat. So this means that the original metric G that you had here is conformally flat, and then you can invoke classical result by Kobayashi-Lafontaine that gives you the classification that you want in the case the solution you have is conformally flat. Okay, so you conclude by the rigidity statement. Conclude by positive mass theorem, the rigidity statement, plus Kobayashi-Lafontaine. Very nice. So, so the only thing that we need to do is try to reply this this situation, try to reply this pattern. Unfortunately, we see, I mean, life is not that easy, okay? And also, before going definitely to lambda equal to 3, let me also observe the asymptotically flat condition. It's really crucial here. I think this asymptotically flat assumption is really crucial because otherwise you have a different solution, okay, with several black holes at equilibrium. Because, for example, here, a byproduct of this proof is that actually the drawing is not the correct one, because a posteriori you just have one single black hole. So this statement is very interesting also because it's telling you basically that you cannot have a static solution with several black holes at equilibrium, right? Because the staticity says that essentially these black holes, they do not attract each other, they stay as where they are. Nevertheless, if you drop the asymptotically flat assumption, okay, if you drop this, you are led to consider also, let's say, this exotic solution, the Myers-Korotkin-Nicolai solution, which are a solution in which you have infinitely many copy of the Schwarzschild black hole. So, etc., etc. So the important thing is that you have infinitely many of them, and they are put at the same distance, so all at the same distance. So that's a way of, okay, so it's a stalemate for black holes. So because they cannot decide whether they have to collapse on this direction or on the other direction, because, okay, and so they are at equilibrium, and you have infinitely many black holes. Of course, these are not asymptotically flat. Of course, no? These solutions are not asymptotically flat. You can, if you want finitely many black holes, you can also cut here and there, and then identify the boundaries. You have essentially a static space-time with a topology of a solid torus minus a certain number of balls. Okay. 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 So in certain sense, the asymptotically flat assumption is essential if you want to have a black hole uniqueness theorem. That's one point. So let me move now, okay, to the situation which is of interest here, which is essentially the one with positive cosmological constant. Okay. So in the case of positive cosmological constant, as I said, we normalize lambda to be equal to 3. So now we consider lambda from now on. Lambda will be equal to 3. Of course, there are results also for negative lambda, but actually I have no time to describe them. So I use the lambda equal to 0 case because it's the richest one, and it serves as an inspiration. So for what can be said for lambda equal to 3? Let me start with the modest solution here, which are the rotationally symmetric one as usual. So in this case, actually, the one that corresponds to the flat Euclidean space is the so-called de Sitter solution, okay? And the space-like part of the de Sitter solution look like this. Maybe green is not the right choice. So you have an horizon here, a boundary, okay, which is still a totally geodesic boundary, but it's a different type of boundary. We comment on this later. And then you have also the corresponding solution to Schwarzschild black hole, which are so-called the de Sitter Schwarzschild black hole. Okay, essentially they are like this. Let me draw the family here for you, and then okay, a little bit less, and then less again. Okay, and you can. I mean, this is a 2D picture, of course. Okay, at the beginning you have. So you start like a half a sphere, and then you have a small horizon there. And this is a Schwarzschild de Sitter metric with a small mass. Then when your mass increases, okay, you have something like this, okay, which with a larger horizon there, okay, and then finally you have something, okay, which is completely cylindrical, in which I mean the size of the two horizons is the same, okay, and here the value of the mass is 0. Here the value of the mass is the maximum one, and which is in our normalization is equal. So this is the maximum value in the description of the family, which is 1/3 square root of 3. Okay, is the usual normalization that it is employed when you want to describe this family. So this one is the de Sitter. And then for m between 0 and the maximum value is the de Sitter Schwarzschild. And then you have the cylinder, which is called in the literature the Nariai solution. Okay. Let me also draw for you also another. So beside the horizon, there is another important place in our analysis, which is the set. Okay, where the lapse function achieves its maximum here. Okay, here it can be an interior point because it's no longer harmonic. Okay, it's an eigenfunction now, and so here you have something like this. Here you have another sphere. Here you have another sphere a little bit larger, and then here finally you have just a cross section of the cylinder, and this yellow part is where the maximum of U is achieved. So in yellow we have the set max of U, so which is U equal to U max. Okay, and in red, I draw what I call the black hole horizon. And in blue is what I call the cosmological horizon. Not me, actually, what is called the cosmological horizon in the literature. Okay, so if you want the explicit form of the metric, actually, so M3 in this time is equal to is diffeomorphic as a manifold to a ball, okay, of some radius r plus minus another ball, three-dimensional ball, centered at the origin of radius r minus. Okay, so this is M3, and GM here is dr square over UM. Formally is the same as we get before, but of course what is different is the expression of UM, which is now equal to the square root of 1 minus r squared minus 2m over r. Okay, if you want to have of course, r plus and r minus are the two positive zero of UM. So at the end, if you want a comparative view of the lapse function, that's what you get. Essentially here is r, this is UM of r, and so you have the Sitter solution, okay? The Sitter solution is something like this, okay? Where the maximum is 1, and also the radius is 1. And in between you have a family like this. So family of solution like this. These are the Schwarzschild de Sitter, okay? Okay, and then the last, so where here you have R plus of M, okay, and here you have R minus of M. And in the middle, you have also the maximum point, which is always equal to M to the power 1/3, okay? And here you have also the maximum, which is U max, equal to the square root of 1 minus M over M max to the power 2/3, okay? Okay, so when M is equal to 0, this value approaches 1, and the value of R minus tends to 0, the value of R plus tends to 1, and when M goes to M max, I mean, the two radii tends to coincide in the middle to the value M to 1/3. Okay, so here's a comparative view of your model solution. So, here the main question is there a black hole uniqueness theorem? With lambda, with lambda equal to 3. Okay, so this is our main question. So one attempt, actually, that it has been suggested in the literature was based, is by Masoud Olam and a collaborator, Yu, and it actually the strategy that they suggest is the following. So essentially, it is very much inspired from this. You start from your static solution, okay, and then you double it, and then you double it twice, right? Because you can identify this boundary with this boundary, and also the cosmological boundary with a copy of himself. And what you get at the end is something like this. So you have something like a ball with an handle, essentially. Let me try to draw it properly. So it's like a ball with an handle. Okay, something like this. Okay, and here you have the two horizons. You have the two identified black hole horizon here. Okay, so here you have the identification of the two black hole horizon, and there you have the identification of the two cosmological horizon. Okay, so by doubling, you get, as usual, a new Riemannian manifold M double with G double. Okay, and then you perform a conformal change of metric, this time based on a green function. So you pick a point. I think they pick a point over there, but you can pick anywhere else. And you pick a point there, and you choose a green function. Okay, this is GP to the power 4 times GD, and this is GD twiddle, okay? And this new metric, actually the claim is that the new metric, essentially here's a green function. So essentially you explode the manifold at P, right, by this conformal change, and you get a new metric that they claim to be, so they claim that M3 double with G double twiddle is asymptotically flat with no negative scalar curvature and with zero mass. Okay, and then if it's so, then you can conclude, okay, by the as before. So conclude by the positive mass theorem, the rigidity of the positive mass theorem, that your manifold should be conformally flat, right? Yeah, because G twiddle is flat, so GD is conformally flat, and so also, yeah, so GD is conformally flat, and use Kobayashi. So GD conformally flat. And also G is conformally flat. Of course, there's a problem here, because, I mean, unfortunately, the conclusion of the rigidity statement in the positive mass theorem gives you that you not only that your metric is flat, but also that you are the Euclidean free space, right, with as a topology. Unfortunately, this manifold is not like this, because if you re-add the point P, okay, you should have a sphere, right? Because if here with this statement and the rigidity statement in the positive mass theory, you conclude that this manifold is diffeomorphic to R3. Okay, it's isometric to R3 with the Euclidean metric. So in particular, it is diffeomorphic to R3. So if you re-add the point P, what you get is a sphere. Okay, unfortunately, if you start with something like this, you get something with topology S2 cross S1. So that proof is not correct. Okay, and yeah. Yeah, because the rigidity statement gives you more than you want. The rigidity statement in the positive mass theory gives you that this manifold is R3.
Conclusion you will not realize, but as a mathematical argument, which part is incorrect?
I mean, the computation is not very detailed, so I mean, it's very difficult to point out a mistake in the computation, but unfortunately there is a mistake in the strategy in this case, okay? Because otherwise you rule out the existence of Schwarzschild de Sitter. I mean, there are several attempts in the years of ruling out this Schwarzschild de Sitter solution. The last one appeared on the website of Invenciones. Unfortunately, we managed to find a counterexample to a technical lemma together with Stefano Borghini, because otherwise, I mean, this solution, there is the extinction.
The part of like the G tilde is asymptotic flat, and with all this condition is not wrong. It should be wrong.
Yeah, one of these three conditions should be wrong. Maybe the fact that max is 0, I don't know, but one of these three conditions is for sure wrong. Yeah, there is also a good reason for this being wrong. Also, the fact that very recently there is some evidence, numerical evidence, I would say, of the existence of exotic solution has been claimed by a group of 4 people: Diaz, Gibbons, Santos, and Wei. This has been published on Physical Review Letter this year, okay, in which they claim to be able to construct static solution, okay, with positive cosmological constant, so solution to this system with lambda equal to 3 and 2 black holes at equilibrium. Okay, so essentially something that reminds you of the Korotin-Nicolai solution, so where you have several black holes at equilibriums. Actually, I mean, it's a numerical proof, so essentially it would be very much interesting to have also a proper analytic proof of this fact. Actually, their intuition is that essentially the cosmological horizon is the gravitational effect of the cosmological horizon is strong enough to to keep the 2 black holes at equilibrium. So essentially, it is. Let me try to give a sketch of the solution that for which they claim to have a numerical evidence. So one of them, here you have 2 black holes. It is a actually symmetric solution. So at the end, I will rotate everything around this axis here. So you have the 2 black holes there, and then you have the cosmological, where's the blue? The cosmological thing, the cosmological horizon here, okay, that keeps these 2 black holes at equilibrium, okay? And so essentially here at the beginning you have spheres, okay? And the set of maximum, so when you rotate you have a sphere here, you have also a large cosmological horizon, and they claim, actually, the picture is not very accurate in the sense that the two black hole horizons are really small and really close by, and the cosmological horizon is huge with respect to them. And actually, the gravitational impact of the cosmological horizon is, as I said, strong enough to prevent these two black holes from collapsing the one on the other. And the set of maximum point here, okay, something like this. It's an S1. Okay, it's an S1. So essentially, okay, believe it or not, I mean, it would be very nice to have also a proper mathematical proof of this interesting fact. And in any case, if correct, this is telling you that somehow you are missing some assumption, right? So and the assumption that is missing probably is about you miss some assumption and also some theorem, right? Because you don't have positive mass theorem and you don't have maybe enough assumption. Maybe there should be something that plays the same role as the asymptotic flatness here, right? So when you have asymptotic flatness, you can conclude. If you don't have this, you can build a solution, exotic solution with many black holes at equilibrium. The same is here, but what's the replacement for the asymptotically flat condition? What's the replacement also for the positive mass theorem? So, there was a suggestion, a very famous one, okay, the so-called Minu conjecture, proposed by Minu in 1995. Let me call as it goes. So the Minu conjecture. Minu conjecture, because it's important to think about this. So if you write the Einstein constraint equation in the Einstein constraint equation for time symmetric initial data, for time symmetric initial data, what you get at the end is that the only thing that you are left with is the prescription that the scalar curvature must be greater or equal than 6, right? So greater or equal to lambda, which in our case is equal to 6. So this is this replaces the condition r equal than greater or equal than 0. So what could be a good replacement for the positive mass theorem, or at least for the rigidity statement in the positive mass theorem? But because at the end, what you really need in this proof is the rigidity statement of the mass theorem. So the Minu conjecture was a suggestion for the rigidity statement in the positive mass theorem. So at the end, you want the conclusion should be, so you start with the manifold, which is just the upper half hemisphere with a metric G, okay? And then by the constraint equation, you assume the scalar curvature greater or equal than 6, okay? Plus some condition. And you want the conclusion that you want to get is the rigidity. So the fact that your S3 with S3 plus with G must be isometric to the de Sitter solution. Okay. So what you have to add? You have to add precisely what could be a replacement for the asymptotically flat condition. So the first one is that at the boundary, you have the metric G at the boundary of S3 plus is precisely the one that you expect in the de Sitter solution, which is just the standard round metric on S2. And also, so this can be, that for a long time has been thought to be the replacement for the asymptotically flat condition. And then there is another condition, because asymptotically flat is not enough. You also want to have mass equal to 0. So the mass, if you remember, I don't write down the definition, but essentially it has to do with the first derivative of the metric at infinity, right? And so the first derivative of the metric at the boundary here is just the second fundamental form, okay? The second fundamental form of the boundary of S3 plus, okay? And being 0 means that the second fundamental form, because the second fundamental form is the normal derivative of the induced metric, right? So 1/2 dgij by dr. And so it is natural to think of this like a replacement for mass equal to 0, whatever the mass is, right? Because, okay, it's worth pointing out that in the literature, it's impossible to find a definition of mass for initial datum with positive cosmological constant. There's nothing beside the fact that everyone called the mass the parameter that appears there in this explicit solution. So that was a good attempt. Unfortunately, this conjecture has been overkilled by a famous counterexample found in 2010 by Brendel, Marquez, and Neves. Brendel, Marquez, Neves. Okay, they disprove this conjecture. Actually, they overkill the conjecture because they produce a manifold, okay, that is isometric to the standard sphere up to there, and then it is something different here, okay, but with scalar curvature greater than 6. So up to so in a small neighborhood of your boundary, okay, you are isometric to S3, and then your metric is something different with scalar curvature greater than 6, but not isometric to S3 plus. So why do I say that this is an overkilling of the conjecture? Because, I mean, no matter how many normal derivative of the metric at the boundary you take, you always get 0, right? Because I mean, you always get the same answer as in the reference metric. So I mean, there's somehow this counterexample shows that there is no way to guess what the mass is, okay, just looking at the boundary here. Okay, so here comes our, so essentially, this is not just a disprovement of this conjecture, but it's also a disprovement of this heuristic, I would say. Okay, so also the heuristic is no longer valid after this theorem. So here is our idea, okay, for try to prove some theorems. So I would like to show you this analytic geometric criterion for finding black hole uniqueness. But before that, let me see which is the intuition for that. So essentially, the idea is that you have to replace the asymptotically flat condition with something, okay, as I said several times. And so by this, so here is lambda equal to 0. Here is lambda equal to 3. Okay, so the attempt was try to use the cosmological horizon, so unfortunately the blue one, and this turns out to be the wrong choice. So our idea was try to say whether it's worth to replace, okay, try to replace the condition at infinity with a condition, with some condition on the set of the maximum point. So maybe the right place to look at is not the cosmological horizon, but max of u. Okay, this is the cosmological horizon. Why so? Well, maybe some indication, some heuristic for that comes from the fact that the lapse function, okay, achieves its maximum at infinity here, right? And here also, maybe it's worth looking to the points where the lapse function is taking its maximum. So maybe you have this heuristic, and since asymptotically flat means that essentially if you were to scale things, actually the geometry that you have at infinity is the one of the sphere, of a totally geodesic sphere. So maybe it's worth, maybe one can, as initial guess, try to see whether what happens whether you impose that the maximum of U is a totally umbilic round sphere. So here you have a statement. So if max of U is a totally umbilic round sphere, then the solution is then M3 GU is isometric to either the de Sitter Sfasci de Sitter, let's say, SDS, or to the REI. Okay? And, okay, at the beginning, when you look at this statement, actually, you seem, I mean, the first reaction is that maybe this is too much, right? Because totally umbilic round sphere means a lot of things about the structure of this level set. On the other hand, if you compare it with the asymptotically flat assumption, it's I would say it's pretty fair, right? Because when you say asymptotically flat, you mean all those things, okay? You mean that at infinity you have essentially a round sphere, okay? Because the metric, the level set of the coordinate function, the asymptotically flat coordinate becomes rounder and rounder, and they becomes more and more umbilic, okay? And so how to conclude here, from here to there? Okay, the idea here is a principle that it has been used also after our contribution, okay? And the idea here is to conclude from here, is to use the Cauchy-Kowalewska theorem, because essentially you look at this, I mean, it is true that the system that you look at is elliptic, right? It's an elliptic one. However, okay, you don't have to prove existence, but prove the uniqueness of the solution, because I mean the solution is given, right? So for an elliptic system, it's not a nice idea to try to cook up an initial value problem. But if you need to classify, then it works. So the idea was to use the right theorem with the wrong equation. So we consider initial value problem for the static system, okay, where the initial surface is max of U, okay, that we are supposing be the total umbilic round sphere. So your data are the induced metric that you assume to be round. So Gij is GS2ij, and U is equal to U max. And also the first derivative. So the first derivative is dGij or by dr. You impose that this is, okay, maybe 1/2 of this. So the second fundamental form is totally umbilic, so is equal to h over n minus 1 gs2 ij. And also that the normal derivative of u is 0, but this is, of course, this is clear. So on sigma equal max of u. Okay, this is clear because it's a set of maximum points. So u equal to u max, and the derivative, the normal derivative of u is equal to 0. It's for granted. And then the only thing that you have to check is that this sigma is non-characteristic, and this is an easy check. And once you have this, the solution must coincide with the rotation symmetric one, okay? Because the initial data are the same. So since everything is analytic, so the only possible solution, the uniqueness theorem in Cauchy-Kowalewska gives you the classification that you like to have. Okay, and actually this technique has been used already in a couple of papers, but maybe I don't have time to mention them. So how much time do I have? 5 minutes. Okay. So 5 minutes. Okay. So so this is not the best result that we have actually. So in general, what can be said about the maximum level set of U, right? So because assuming all these things may look to be too much, even though it's not that unfair, let's say. So the idea is to use the maximum point, the set of maximum point, to cut your manifold into region and try to guess what's the mass of each of these regions. Okay, so what can be said in general about the maximum level set of U? So in general, it is a level set of an analytic function. So a priori, it is a stratified manifold. So what can be said about the max of U? Max of U in general, it is, as I said, a stratified analytic set. So a priori, it has a top stratum. So it could be something very weird, something like this. So imagine you have an 8, okay, with foliated by 8s. Okay, so you have several 8s. They become eventually smaller and smaller. So essentially, at the end, you have something like this. So it should be something very weird, okay, with different strata, okay, 2-dimensional strata, 1-dimensional stratum, 0-dimensional strata, so points, okay. And the first thing that we have is a regularity result saying that the max of U, you have the regularity lemma, saying that the max of U in our case is given by a top stratum and a low dimensional stratum, but the top stratum, so this one is 2-dimensional, sigma is 2-dimensional, gamma is dimension 1 or 0, so this is stratified, and this one is smooth. So the regularity is that the top stratum is smooth. So if you have a top stratum, then you can use it to cut your solution. So a priori, you have a solution that looks like this. So a priori, you have several boundary components, okay? Several of black hole types or of cosmological types, okay? Maybe you have some topology inside, okay? But then you consider the max of U, and the top stratum with the max of U can be used to divide this manifold, to cut into pieces, to cut into regions. And for each of these regions, so you have a region here, you have, for example, N1, N2, N3. Oh, this is not the case, sorry. Because the top stratum is regular. Okay. Okay. What we'd like to do is essentially find the appropriate notion of mass for each of these region. So the idea is to analyze each region separately. Okay. So first thing so I have not time to describe the notion of mass, but essentially I tell you the idea, the rough idea is to look at the surface gravity. The surface gravity here is just the value of the gradient of u. The gradient of u has constant length on the boundary, okay? And the same happens in the model situation, of course. And you compare with the value that you get on the model situation, and then you say that the mass of a region is the same mass that the same number that you have on a model with the same surface gravity, essentially. Okay. So essentially, so we have a theorem that says that for each n, okay, which is a connected component of m minus the max of u. Okay, you have for each connected component of m3 minus the max of u, you have a number m of n which is non-negative, okay, and which is 0 if and only if your solution is the de Sitter. Okay, and this number can be regarded as the mass, and this can be regarded as a sort of positive mass statement for static solution. So let me skip to the final result that I want to mention. Okay, so you can use this invariant here, this mass that you can define also to prove area bounds, sharp area bounds, so sort of Riemannian Peretz inequality for each of these horizons. Okay, but I have no time to quote them. The only thing that I like to mention is the final statement. So what is our black hole uniqueness theorem? So suppose you have a two-sided solution. This is the last theorem with Borghini, Cruciel, and myself in 2023. Okay, so essentially, suppose you have a two-sided solution here, not three-sided, but two-sided. So suppose I say this and then I stop. So suppose that you have a two-sided solution. So with so suppose you have a solution, and suppose you have that the set max of u is disconnecting your manifold into two pieces. You call one n plus, the other one is capital N minus, okay? And the black hole are all on one side. So maybe, so this is an inner, you may have some cosmological horizon here, but the important thing is that on n plus you only have cosmological horizons, okay? The one with low surface gravity, okay? And if you have this, you can define the mass m plus of this quantity. This is, you can define mu of m plus, and then here you can define mu of m minus, f of m minus. And the theorem says that they coincide. If they coincide, if the mass of m plus is equal to the mass of m minus, then your isometric, and they both coincide with a number m, then you are isometric to the Schwarzschild de Sitter solution of mass m. Okay, so I have no time for the proof, but essentially it is based on comparison arguments. So essentially, yeah.